That's called alpha decay. The second type of decay is represented like this, and it's supposed to have a long tail on it. It's the Greek letter called beta. So this one's called beta decay. Now, this one's tricky, so you have to watch me very carefully how I do this one. Okay, very, very carefully on how I work this problem. Okay, now you're going to have to really watch. Let's use this example. Let's say we had a proton. Actually, let's do it this way. Let's say we had a neutron. That's the best way to do it. Okay, neutrons are neutral. They're found in the nucleus. They don't have any charge at all. They just give mass to an atom. That's all they do. And we talked about in one of the other videos. But sometimes a beta decay occurs in an atom, and here's what scientists think really happens. Scientists really believe that a neutron is really not just that. They really believe that a neutron is a proton with an electron stuck to it. Now let's think about that for a second. If you had a proton and you stuck an electron to it, positive and negative, it would be neutral. And electrons really don't have hardly any mass at all. So really, overall, that would be a neutron. And so you have this proton with this electron stuck to it. All right, so I think that makes sense. And what happens in a beta decay is actually this thing snaps off and flies off. Not the proton part, but the electron breaks off, flies off very fast. Now the question is, when this flies off, trying to get the atom to be steady, is it a neutron anymore? Well, no, it's not a neutron anymore. It now counts as a proton. So it used to be a neutron when it had the other part on there to balance out the plus, but when that electron flies off, it's really a proton. Let me see if I can do it mathematically for you. The most common one in the world is carbon-14. Carbon-14 is one you learned in your social studies class. This is how they date old objects. Like they find an old bone and they can approximate how old it is. It's called carbon dating. And so in this example, it's going to go through beta decay. Now, here's how it's mathematically written. Now, a while ago, it was a 4-2 helium. It was a group of 4 with 2 protons, and that flies off. Well, in this case, it looks like this. O, -1, beta. Now, think about it for a second. -1, an electron's a -1 charge. That's where it comes from. Okay? And an electron doesn't have any mass, so that's why it's a 0. And let's just do the math. Let's not worry too much about anything. What plus 0 is 14? Well, simple math says that's 14. So 14 plus 0 is 14. Now, this is tricky. What number minus 1 gives you 6? 7 minus 1 is 6. Now, this is interesting. It actually went up overall. Now, remember, that neutron we just talked about isn't called a neutron anymore. It's that proton when that electron flies off. So it doesn't count as a neutron anymore, but it now counts as just a proton, so your proton number goes up. Okay? So here's what happens. On the periodic table, carbon-14, which happens to be radioactive, because normal carbon is a 12, carbon-14 moves up to 14-7. 7 is nitrogen. Beta decay. Now let me show you one more of those real quick on the periodic table. Let's pick something like neptunium, 237-93. When it goes through beta decay, numbers. Well, this has to be 237 as it adds back. This is going to go up to 94. So when you look at the chart, plutonium, 94. Simple math tells you what to do. You'll always have a periodic table to help you. And so beta decay looks like this. Okay, now we'll put them together here in a minute, make your life a little easier. So let's talk about the third one real quick. It's called gamma decay. There's the letter for it, gamma decay. Okay, and really most times they're not going to even give you the letter, so we'll just talk about gamma. Gamma's the easiest. Gamma decay in a nuclear breakdown of nuclear decay is the energy that's given off. That's all it is. There's no numbers that goes with it. It's just the energy. So the idea is this. Whenever you have a nuclear bomb, for example, hit the ground, and the atoms start breaking up, what happens is you're actually going to have not only particles breaking up, but you're going to have tons and tons of energy. So let me explain real quick. We had the nucleus like this that we were doing a while ago, and we had the alpha decay that was sitting on here. When alpha decay happens and it flies off, that's normal. But if you were to drop this on the ground and every single one of them all broke up at one time, what you're going to end up having is tons and tons of energy. And that energy is what is going to cause the damage. So alpha decay, beta decay each have a mathematical formula. Gamma decay is just going to be energy. What I'm going to do in the next video is you're going to actually practice, can you do alpha decay, beta decay in real nuclear reactions?